Welcome to the NOAA Science Seminar, Long Endurance Subsea Marine Robotics, Technologies, Applications, and Lessons Learned. This presentation will focus on the results from several projects that address challenges of multi-vehicle approaches, novel operating paradigms, and targeted technology development. This seminar series is co-hosted by NOAA Ocean Exploration and the NOAA Library. My name is Nina Przinski, and I'm the Grant Science Support Coordinator working at NOAA Ocean Exploration in the Science and Technology Division, and also with the Ocean Exploration Cooperative Institute. I'm really excited to introduce you to our seminar speaker today, Dr. Michael Jakuba. Dr. Jakuba is an engineer with extensive experience designing and deploying marine robotic systems. He received his PhD in mechanical engineering and applied ocean physics and engineering from the Massachusetts Institute of Technology and Woods Hole Oceanographic Institution Joint Program in 2007. He was a postdoctoral researcher at Johns Hopkins University and the Australian Centre for Field Robotics in Sydney, Australia, prior to returning to Hui in 2011, where he now works as a senior engineer. Dr. Jakuba's initial project was supported via the NOAA Ocean Exploration Fiscal Year 2018 funding opportunity. So without further ado, I'd like to thank you, Dr. Jakuba, for your time today and for choosing to share your work with us. So I'll hand the mic over to you.
Great. Well, thank you, Nina. Thank you, Cassandra. I really appreciate this opportunity, and I appreciate all the support from NOAA over the years. Most of what you're going to see today is not just the project that Nina mentioned, but others that have also been funded by NOAA, and it's been a real great pleasure to work with many wonderful people at NOAA. So again, thank you. Right. So today I want to talk about long endurance subsea marine robotics. As Nina mentioned, I design and build various undersea systems, particularly vehicles and certain subsystems. But one of my interests for a long time has been in the development and use of long endurance subsea systems. So that's the topic that I'll discuss today. So why long endurance? I don't think this is news to anyone, but cost and scaling improves with reduced dependence on ships. Right. So and that has some interesting implications. Getting rid of the ship has some interesting implications in that shipboard operations tend to favor fast and high power systems, whereas eliminating the ship reduces that time constraint and it opens up the possibility of what you might be able to do with other systems. There's, of course, a question of access as well. So ships limit things to certain weather windows. It's difficult to get to remote regions. The deep ocean sea floor is harder to access, whereas under ice is potentially impossible to access. And increasingly, there's nearshore infrastructure, wind farms, and so forth that can also limit ship access. So the questions I've been looking at are, at least in this context, are what seafloor survey and exploration methods that are in use by conventional AUVs and ships might be done without a ship, and what are the impediments to doing that? And with the risk of being a little bit controversial, but hopefully just stimulating some discussion, I would say that there's been really explosive growth in autonomous surface vessels, different types and different capabilities over the last couple of decades, and that really hasn't been matched by undersea systems. So for sure, the workhorse long-range platforms of Argo floats and gliders are well established with long-running programs and many systems out in the field, but they're not focused on the seafloor, so they have a very defined mission. There are some examples of long-range AUVs. I've highlighted two here from the AutoSub long range and the Mbari LRAV, which I'll talk about more in a bit. But the number of units, not only the variety, but the number of units out there is much smaller than the number of ASVs. So let's talk about some of the fundamentals here. The endurance of undersea vehicles is, of course, constrained by how much energy they can carry. That comes from the fact that there are really no practical sources of high density, by which I mean hydrocarbon energy or environmental energy available subsea. Again, practical being a key term there. If you ignore the sensing, or what I'm calling the hotel load here, then you can quickly arrive at a very simple equation for how range scales as a function of certain vehicle design and operational parameters. And what you get is this here, which I'll call the range equation, which is that range is proportional to the volume to 1/3 power, or equivalently a length scale like the diameter, divided by the speed squared. This is ignoring that sensing load. If you include that, then you get this kind of plot from Bradley et al. In 2001, which I'll call the Bradley curve, which basically penalizes going too slow. So if you go too slow, then the energy is consumed by running your sensors or your other hotel loads. If you go too fast, then you're burning all your energy overcoming drag. And somewhere in between is this optimum speed where you maximize range. What these two things mean for long endurance systems is that you have two basic options, at least if you're just talking about one system in isolation. Either you can go slow and have a very focused and low power application, and that's basically what gliders and floats, the approach that they take, or you can be very big and have maximize your volume or increase your volume and thereby have more energy to work with. All right, so the range equation is fundamental, and I'm not proposing any magical solutions to it, but it can be mitigated with various strategies. So in that light, I want to present 4 different case studies with the sort of following themes. So first of all, what can you do by teaming ASVs and AUVs? Baseline, that can yield some force multiplication, even in the context of ship-based surveys. I'll talk about a project that was attempting to improve the navigation for low-power platforms, in particular gliders, so you can get around some of the sort of mission limitations that those systems otherwise face, and also as partial substitutes for ships, again to accommodate some in the same line to take some of the responsibilities that ships have and replace them with systems that don't require ship on site. Also talk about a couple new payloads and applications for nearshore launch platforms from some fairly recent demonstrations. So one is offshore bathymetric survey. This is a good one because it involves a fairly high power payload in the form of a mapping sonar, where increasing the battery capacity was the right answer. And the other example is some benthic fisheries survey work that we've been doing with Northeast Fisheries Science Center, where we're using a medium-powered payload, but sort of carefully managing power by modifying how the mission is executed in order to get that long range. There are, of course, many other solutions that I'm not going to talk about, but just briefly, diving ASVs that spend some of the time on surface and then collecting energy and then dive, docking to recharge vehicles. Hybrid gliders offer various interesting possibilities. Making actually the ship's autonomous, something like what Ocean Infinity does. It represents a certain kind of state of the art if you can afford it. Marsupial systems may allow for vehicles to harvest energy subsea from their surface asset. And then, of course, better batteries in some respects represent a holy grail. But for now, anyway, there seems to be no practical solution that's superior to lithium ion and lithium primaries. All right, so case study 1, to jump right into it. This is tending AUVs with ASVs. This is an endurance adjacent project, let's say, not really about long endurance per se. Only one element of the system that we put together here is long endurance, the surface asset, wave glider, whereas the AUV was a conventional sort of 1 to 2, maybe 2 day at maximum survey platform recovered and launched by the ship. The idea is simple: pair an ASV with an AUV to monitor and perhaps navigate the subsea asset. But with launch and recovery still from the ship. The motivation is to free the ship to perform other work while still maintaining the ability to monitor mission progress and increasingly to modify the mission, perhaps communicate with subsea autonomy as well. Nothing about this was in question technologically when we did it. Many groups have done it and continue to do so. But I wanted to share some of my experiences in doing this because I think the lessons that I learned really feed directly into the work that's really focused on long-range applications. All right, so this was a cruise back in 2018. It's fairly common in the National Deep Submergence Facility to pair Alvin operations with Sentry operations. So Alvin runs during the daytime, and Sentry runs as a night program. So a nice complement of seafloor sampling and inspection, and then mapping in between to provide context. The idea was to insert a wave glider into the mix to act as a tender for the Sentry AUV, with again the goal to free the ship to be able to do other things without losing oversight over what the AUV was doing. Again, not technologically in question. The question was whether it was sort of operationally and culturally feasible. Would the Sentry operations team be able to handle the extra load of dealing with another vehicle? So we had a pretty successful cruise. The Sentry dives are on the right here. It's about 20 dives, and each shown in a different color. The wave glider was deployed at the beginning of the cruise. Was collected briefly at one point for a hardware change, but otherwise spent the entire cruise in the water. That was critical to minimizing the load on operators. And we just moved it between sites. We could do about 10 to 20 kilometers a night between sites. And that worked really well with this sort of 24-hour operations pace. But we had our biggest success, I think, when we altered when we thought a little bit harder about sort of optimizing the system. So this example, the upper plot is showing the range between the ship and the AUV in orange, the range between the ship and the ASV, the wave glider, in yellow, and then the AV depth in blue. So rather than a 24-hour cycle here, what you're seeing is a 48-hour cycle with the AV spending 36 hours on the seafloor. So rather than recovering it for the Alvin operations, it stayed underwater and continued to do its survey. By utilizing the Bradley curve for the Century, we were able to find a speed which yielded actually a 38% improved seafloor coverage rate. So that's not seafloor covered per dive, but rather the overall rate, if you include however long the dives are, relative to operating on a 24-hour schedule, plus providing some number of hours, 4 to 6 hours, for off-site coring. So you got kind of that bonus time, that force multiplication in a sense, but actually got more of the data that you were out there to collect in the first place by optimizing these sort of range equations. In addition, there was negligible degradation in map quality and no loss in operator awareness. The wave glider in this case was not providing any kind of navigational aiding to the AUV. So the AUV was navigated to the seafloor using the ship's USBL to accommodate that period of time when it's not in bottom lock range, and then from that point on relied on its very high-end navigational suite to produce a very nice map. We've done some 5 Century cruises since, and permanent integration of a more modern wave glider into the NDSF is underway at present. Of course, that begs the question, could you do navigational aiding from an ASV? And of course, the answer is yes. Our particular foray into that realm was with a project with Northwest Fisheries Science Center and their AUV Popoki. So in this case, the need for navigational aiding is much more acute because this system, unlike Century, does not have a very high-end navigational suite. In particular, does not have a north-seeking gyro compass. And by providing navigation, so navigation is required during the time on the seafloor as well as during the ascent and descent. And by providing that from the wave glider in the form of Evologic's USBL, we gave the ship a little bit more time to go off station and do this sort of force multiplication thing. The other element of this project that I think is important was to push this idea of keeping the of limiting the impact on operators. So in the Century case, we kept the AV in the water for the duration of the cruise. If it had been recovered and launched on a regular basis, I think it would have been an immediate loser. But you can take that one step further and not put it on the ship or deploy it from the ship at all. So in this case, we deployed the wave glider several weeks ahead of a planned rendezvous with the Shimada and the Popoki AUV off the coast of Oregon. The vehicle transited south and then waited there. The Shimada eventually arrived, and we did one dive where the vehicle was tended. Unfortunately, the ship had to immediately depart station on account of some other problems after that, so we didn't get more chances. But nevertheless, it demonstrated this concept of using a long-range ASV as a kind of on-call asset that doesn't require the AV operators to touch it or really know much about it. So the nice thing is that you can have your ops team associated with the wave glider completely shore-based, do the launch and recovery at sort of their leisure, and move a lot of the tending responsibilities to shore. In the end, the vehicle we spent about 2 months at sea, covered almost 2,000 kilometers, most of that actually holding station, waiting at these rendezvous points. So it's potentially viable to put a system like that out for a season and have it available again on an on-call basis. All right, so some lessons learned from this. The impact of this kind of ASV tending is enhanced if you can find ways to collect more baseline data, the data you're out there to collect in the first place, seafloor maps in the case of Century. So we should look for opportunities to modify normal operations to yield more, better, or new kinds of data by modifying the cadence of operations, for example, or mission parameters. In terms of force multiplication, minimal impact on normal operations is absolutely key, or otherwise the benefits potentially provided by adding an ASV in this capacity instead become a burden. I think long-range assets, ASVs, there are many of them now, are the perfect fit to this in the sense that they don't have to be necessarily handled by the ship at all. If you add shore-based piloting to that further eases the at-sea burden. I'll add one more thing on the first point here is that That change in cadence also reduced the amount of effort that operators had to put into operating Sentry itself, because it was only recovered half the time. So the biggest win here to look for is if the burden of operating the baseline vehicle is eased. Again, moving operations to shore or reducing the number of launches and recoveries. Right, so we'll move on to the case study 2. So this was a project, and actually the one that Nina mentioned, focused on trying to use or trying to enable low power platforms, gliders in particular, to do things that are typically reserved for AUVs. The particular challenge to be addressed here was the navigation of subsea gliders. So to understand the value of this, you got to understand how gliders are navigated now. Probably you presumably already know this, but in any case, gliders start at the surface. They get a GPS fix. They use a model to dead reckon on their way down, and then they come back up. They get another GPS fix, and then they compare the predicted location based on that model to where they actually ended up. Use that to compute a so-called depth average current, or DAC, which then gives them a sort of post-dive estimate of where they were over the course of the dive. And for near surface or mesoscale or larger processes, this has proven to be an excellent solution, and it requires absolutely minimal power. So we asked the question, though, what might better navigation yield? Well, even in the context of physical oceanography, you could potentially get current profiles if you were able to navigate the system throughout the water column rather than this depth average current. And in places with complex flows, like around seamounts or complex topography, additional navigation could potentially be useful. Outside of the physical oceanographic context, exploration and the deep sea floor in particular, hydrothermal prospecting is one application. That's the concept in the drawing here. Hybrid gliders offer interesting possibilities of moving between water column mapping and seafloor mapping. So the way that the one-way travel time inverted USBL system works. Our solution was a one-way travel time inverted USBL system, and particularly focus on a low power one. There are inverted USBL systems out there. Our focus was to make one that was sufficiently low power that it could run on a glider without significantly impacting its endurance. So the basic idea is this: the surface asset sends out an acoustic pulse. One or more gliders subsea receive it at an array. That array is able to compute to measure the azimuth and elevation of the incoming sound, from which, and both topside asset and subsea asset have synchronized clocks by using either a temperature compensated oscillator on the part of the AUV, or for additional precision, a atomic clock. And from that, you get your range and your azimuth. You can get elevation either from the array or from your depth, and that gives you a position relative to the surface asset. If the surface asset also sends its position, then you can get your geodetic location. So one other element of this diagram that's important, so you see that the gliders here are not returning to the surface, so they're not getting GPS fixes. That's enabled by using a system like this. But also, if you're interested in the deep sea floor, then this is less time spent in the portion of the water column that you don't care about for this particular application in any case. All right, so prior to the start of the project, we did some reasonably detailed analyses on the feasibility of actually doing this from a power perspective and what we could hope to gain. And what we found, that navigational accuracy on the order of hundreds of meters, working at thousands of meters depth, was possible for modest power consumption. Modest in this case meaning somewhere on the order of what the glider is consuming anyway in its hotel load. So the plot on the left shows you a little bit more detail on the performance that we expected. The upper line here is a glider that is notionally coming to the surface just every 5 days. This is dead reckoning performance, essentially. So the time is the only portion of this that matters. The depth doesn't matter if you're just coming up every 5 days. The second line is for a glider going to the surface starting between profiles, so profiling to 500 meters or profiling it to 6,000 meters. And in this case, the time is changing because the amount of time spent doing the profile is increasing as you go deeper. And then the two curves here are for two different scenarios using an IUSBL system. And time is no longer the issue here because each fix gives you a geodetic position, but the quality of that still matters with range, with, of course, longer ranges resulting in reduced precision. So it just so happens that you get a similar curve out of this because range and time are related by the speed of the glider. But in any case, what you see is about an order of magnitude improvement over what you might expect based on dead reckoning error, typical currents, and so on. Another element of this is that of course, carrying the system does incur. I missed an important point. The reason you can do this for low power is that this system is only receiving, right? It's never transmitting. It's the one-way travel times rely on precision clocks, which are low power in comparison to transmitting acoustically. So it's suitable for low power platforms like gliders. But there is nevertheless a penalty. And the question is, how big is that penalty? Well, it turns out that if you're focused on this sort of deep profiling use case where you're focused on the deep seafloor or the deep water column, that you can actually get more data within the depth band that you care about than you would otherwise, even though your overall endurance is, of course, reduced. All right, so here's what our hardware solution looked like. On the left is the array, so four element array with a preamplifier built into this potted construction here. On the back side is a small housing containing an attitude heading reference system, and that's a really critical part of this. Bolting these two together mechanically meant that you can you significantly ease the integration effort into platforms that can use this, because you're not worried about using the attitude from the host system, which can be subject to either, in the case of gliders, only being available at fairly low rate, or mechanically being not particularly well calibrated relative to wherever you might be able to mount this. There are other, so the other electronics live inside the main housing of the Sea Glider, which consists of a Hui micromodem, a C-scan, a temperature compensated oscillator, the clock, which is the only part of the system that has to remain on. Everything else can be shut off between detecting. And then a backseat computer, and I'll get back to that in a minute. But the backseat computer was not something we hoped to have in the system initially, but turned out to be really critical for development purposes, and ultimately, hopefully, can be eliminated. Our initial sea trials, the ones depicted here, were with the system just as a payload. We also did a number of tests on other platforms where we had the benefit of ground truth, so we could do a decent characterization of the performance of the system, from which we got an azimuthal precision of about plus or minus 5 degrees, that being really the critical number. And that's pretty much in keeping with what our initial predictions suggested. All right, so the next step was to integrate the system with the actual control system, because ultimately we want to be able to coordinate the motion of these subsea platforms with the surface platform. And that can be challenging with these kinds of platforms, which are really optimized for low power navigation. And while they're intended to have instruments incorporated into them, they aren't necessarily intended to have instruments that also require feedback and issue commands potentially to the control system. So in particular, sea gliders do not typically change their heading subsea. They're controlling, or their heading goal, subsea. They do control their heading, but the heading goal is one number. So we had to work out a way with collaborators at APL, who are fortunately PIs or co-PIs on this project, to do that subsea. And what we ended up with was a sea glider that was able to home to a beacon, in this case on a boat. You do get this kind of squiggly trajectory out of it. That's because of, again, this sort of low power constraint. The glider only controls periodically and has large deadbands. And then the project culminated in a 10-day deployment off Newport, Oregon. So we were working at a place called Carbonate Ridge, which had about the right depths. It was 500 meters deep, and also relatively safe with respect to the shipping lanes. So all these lines are AIS tracks from ships. We had a sea glider and a wave glider out with us. You saw on the previous slide 2 wave gliders equipped with the USBL system. Unfortunately, one of them failed just before field trial, so we only had one. But otherwise, other than the shallow rating and 2 wave gliders, or 2 sea gliders rather, we were able to demonstrate the essential elements of this concept. So just some performance numbers. So on the left is the IUSBL performance from one dive number 110 out of about 120. What you see is the GPS location of the glider at the start of the dive. Its dead reckon position. This is with the depth average current correction applied, so that the track ends up at the GPS location upon surfacing. In green is the IUSBL fixes. These are unfiltered, so raw during the descent, and then in brown during the ascent. The pitch of the glider, of course, changes, and the array is mounted on there such that it's roughly level during a typical 20-degree descent, and then ends up being at about 40 degrees during an ascent, and performance is generally better during the descent. So while it is noisy and there are some systematic outliers in here, what's important about this is that there is a systematic difference between the dead reckoned, again, this is corrected after the dive, so it would be larger otherwise, and what the USBL shows. And so you can start to resolve some structure in the current relative to this depth average current out of the sea glider, out of the IUSBL position. There's work to do here to improve the noise characteristics, but the signal's there, and we know it is because if one very high precision element of the system is the one-way travel time. So between one-way travel time and high precision range, you get a comparison that you can compare that to the distance between the dead reckoned trajectory in blue, and you can see that there is a systematic difference. All right, so on the right is it demonstrates the coordinated motion between the ASV and the glider. So the wave glider is here in black doing its kind of typical orbits. The sea glider had the mission here of trying to get underneath the wave glider. And so each of these dives, the yellow is shallow, the blue is deep, had the sea glider essentially homing to a sort of virtual waypoint underneath the wave glider. When the vehicle returned to the surface, there was a strong surface drift to the west. So each dive required the vehicle to make progress back towards the wave glider. But we could move the whole system together by moving the wave glider progressively to the north, and the sea glider followed along the way. All right, so lessons learned. All right, as I kind of mentioned, integration into specialized and optimized platforms can definitely be challenging. We really benefited from having co-PIs at APL on this so that we could work with them directly so we could work with engineers that had their deep knowledge of the sea gliders. There's not really a lesson learned, but it's more of a statement of potential here. The benefit of the system really goes up as you go deeper because the dead reckoning error increases so much. And there is, at present, the situation has changed since this project was funded. There is no commercially available deepwater glider at the moment. We are in talks with Teledyne about a project that might resurrect some of their efforts in that direction. So we'll see. All right, case study 3. All right, so the goal here was to demonstrate offshore bathymetric survey with nearshore launch and recovery, ideally without a ship. I've put shipless here in quotations because this being a demonstration, we did have a tending ship, and that had some implications for how the demo went, as I'll get into in a second. But our two core components here were, again, the wave glider and a Remus 600 mapping AUV, so suited to bathymetric mapping. In this case, it was equipped with an EdgeTech interferometric side scan sonar. There are several elements to doing high quality bathymetric mapping, which you all are very aware of, but many of them are actually handled by the tending ship in the case of using an AUV for this. So we wanted to recreate as much of that as we could using autonomous systems to eliminate the need for the ship. So there's several elements of this. Firstly, if you're going to launch from shore and avoid the need for a large ship or offshore vessel anyway, then the system elements need to be capable of transit to and from shore with meaningful time on station to actually perform the survey. In our case, our requirement was a transit out to the shelf and back, so 200 nautical mile round trip transit from Woods Hole, plus 24 hours surveying on station. Secondly, you need navigation between the surface and bottom lock height, in deep water anyway. For that, we used the same IUSBL system you've seen in the previous case study. I won't talk any more about it here, though. Infield QA QC is really valuable, although the time constraint implied by using a ship is somewhat relaxed. It's still a lot of effort to get a vehicle out into the water and a lot of time spent in the water to come back with no data or corrupted data. So we wanted to make sure that there was a way to QA and QC data being collected from the survey area without, again, needing a ship on site. So that required this kind of data offload process, which I'll go into, and then telemetry of that back to shore. and the ability to modify the mission and sonar parameters, for example, from shore. And then, of course, we wanted to just replicate the mission monitoring that is typically done by ships and enable that to be done from shore. All right, so this was the plan. Transit out to the shelf break, do survey, and transit back. Total time of around 96 hours, 100 nautical miles in either way, and a 24-hour survey in about 500 meters of depth, limited by the depth rating of the REMA 600. As an element of this, we also wanted to demonstrate the picking of routes that would minimize energy use so that you could extend your survey as much as possible by taking into account the background currents. Now, the weather off the coast of New England in November had different ideas. So we ended up with a demonstration that was a little bit smaller in scale, although many of these track lines that are shown on the left here are doubling out and back so that we still got the same, nearly the same overall track over the ground in terms of distance traveled. But we had to modify where each of these elements were going to happen. So what we ended up with was a transit out to one of the wind farms, a transit back. The survey itself was done inside the sheltered waters of Buzzards Bay. And then the vehicle went back out again and then came back and we concluded the whole thing with that optimal route planning experiment, which I'll get into in a second. So the concept was for the survey was that the ASV would be waiting on site. The AUV would arrive on site, establish acoustic communications with the ASV, then perform a patch test, come to the surface, create a high bandwidth link with the ASV, allow operators to download some data from the AUV, and then while that's being transmitted to shore, commence the survey. And after that point, the AUV could call the ASV back, so the ASV could call the AUV back to the surface if necessary, or otherwise just provide the normal tending and navigational aiding, as we saw in the first case study. All right, so in this case, the solution to the range equation, if you will, was more batteries. It made sense because this is a relatively high power payload, relatively high power vehicle, and most importantly, adding another tray of batteries, as was done here, did not fundamentally change how one handles the vehicle. Required a crane anyway, so you're not having a big impact on the concept of operation. Let's see. So in terms of hitting our marks, the mission ended up being 72 hours rather than 96 hours, but we had 35% battery remaining, which exceeds that 96-hour runtime that we were aiming for. So this is a system capable of accessing the shelf break for bathymetric mapping. The data transfer process. So again, this involved the AUV and the ASV creating a high bandwidth link over Wi-Fi near the surface, so they had to coordinate their motion to get within range of one another and then loiter within range of one another. That relied in part on the ASV transmitting its position acoustically to the AUV. Once within Wi-Fi range, they made that connection, and then operators could log in via Iridium Certus through the Waveglider to the AUV, download data from the sonar back over to the Waveglider where it was buffered for transmission back to shore. At that point, the AUV was free to continue on its survey, and then we had to wait for the data to come back before we could decide that it was actually good. This was definitely the Certus connection was definitely the big bottleneck in the process. I mean, that's being relaxed rapidly with low Earth orbit satellites, so that's probably going away, but it was good enough to demonstrate the concept. All right, final part of this was the use of simulation to aid in selection of optimal paths to and from shore. So the motivation here is that long range and particularly slow assets are more affected by currents than by relatively strong coastal currents than you find in the open ocean. So path optimization can yield more time on station. The challenge with respect to currents varying rapidly is that the precise schedule of when a vehicle might pass through an area is not known, and conditions, of course, change. So you need to be able to make these decisions fairly quickly. Our solution was to simulate any number of trajectories in the cloud, such that we could handle essentially arbitrary complexity, although in this case it was limited to just currents from the NECOFS modeling product. And we could run any number of of simulations concurrently, so we could examine several paths. This was all done on Amazon Web Services on their RoboMaker platform. So here we've got two potential paths, path A and path B, path A through Buzzards Bay and path B through Martha's Vineyard Sound. The idea was that the vehicle, upon approaching what's labeled here as BB0, would make a connection with operators to indicate where it was, and with enough time for us to run these simulations with the current best predictions and an estimate of when the vehicle would arrive at BB0 in order to give it a decision as to which path to take. So in this case, as you can imagine, the choice is fairly obvious for a vehicle this close. There's a strong, fair tide in Martha's Vineyard Sound, a little bit less of one in Buzzards Bay. But as you increase the scale, that may become less obvious. And so I'll just run the simulation output for you here. So the two red dots chasing each other or racing each other down path A and path B are the initial simulations we ran. They showed pretty clearly that Martha's Vineyard Sound was the right answer. The other two dots here are closer to what actually happened. So we missed our mark by about 20 minutes in terms of when we thought the AUV would arrive. The answer is still the same. The right answer was through Martha's Vineyard Sound. But so the simulation here is not particularly complicated, but what's important about this is that we were able to run this kind of simulation on a time scale that's relevant to actual operations. So these were executed in field, 20 minutes ahead of the need to make a decision, again, using the cloud. All right, so lessons learned on case study 3. We weren't able to get offshore. Ironically, that was because we had a ship with us, right? These platforms would have been just fine offshore. And it's certainly true that, for example, the Wi-Fi performance probably would have gone down in the conditions we were in, but that wasn't the bottleneck we faced. So I think the second thing is that platform reliability, and this is true for all of these, of course, is critical. And we benefited in this case from really high maturity of the Remus platform and also some ability to do onboard fault handling. So at one point, the system needed to reboot, but it had all the right hooks in place to did this on its own and had all the right hooks in place to start back up where it had stopped. If you're used to working with AVs that run on a 24-hour basis, they don't typically have the ability to recover what they were working on previously. They need a new mission loaded. All right, so our final case study is concerning these Embare long-range AUVs or LRUVs that we're operating at Hui. I want to be sure to give credit where credit is due on this project. So these are Embare design vehicles. What we are doing is we're operating 3 of them, and we're integrating our own payloads with them. They were brought to Hui by James Bellingham and Amy Kakulia. I took over that group after Amy's departure in 2023. So the project that I'm going to talk about was started by Amy, and I want to make sure that she gets credit for that. I think we've done right by that, and it's been productive in a continued collaboration with Northeast Fisheries Science Center. These vehicles are really suited to water column work. We've tried to push that a little bit by building a system called ABIS, which I'll get into in a second, that's focused on seafloor imaging. All right, so these vehicles are designed from the ground up for long-range operation. They are very low drag and operate at a moderate speed. As Jim Bellingham told me once we were discussing this design, if you want to do low drag, you got to have religion. So there's a lot that goes into that. The high aspect ratio fins, optimized tail cone or afterbody, and matched propeller. There's a buoyancy engine, which allows for the vehicle to ballast itself to neutral, which combined with a mass shifter to trim itself out allows the vehicle to fly at zero angle of attack and avoid while transiting and avoid the parasitic drag that would otherwise be incurred. Nominal range is about 1,000 kilometers in its sort of base configuration. That's limited to sort of fluorometers and PAR sensing, for example. It occupies an intermediate design space, I would say, between gliders and typical mapping AUVs. So it's higher power payloads are possible. It's a bit faster. Those, of course, come at the expense of endurance, but it's still 2 weeks or so, and that's long enough to be able to do long transits, potentially out to a site where you can turn on your relatively high power platforms, and that's the way we've been using it. So the particular context is the scallop survey. We've been working closely with NOAA Northeast Fisheries Science Center. The scallop survey or the fishery is about a $400 million a year industry, and it relies on a yearly survey that looks at biomass along the entire scope of the fishery. That has been done for a long time with trawls, and then somewhat more recently with a towed camera survey using a system called the HabCam. But with the advent of wind power on the East Coast, those methods are facing certain problems. So, in particular, trawling is not possible through wind farm areas because of the seafloor cables and the proximity, or the distance between the monopiles that support the turbines makes towing systems through there potentially dangerous. So the question that fisheries came to us with was whether we could essentially replicate what HabCam does on an AUV. And what resulted from that was what we call the Autonomous Benthic Imaging System, or ABIS payload. The intention here is to reproduce the geometry and metadata that is produced on the imaging geometry and the metadata that's produced on the HabCam on an AUV system. So it's got a stereo camera pair with the same baseline, 4 strobes, which are necessarily a bit closer than they are to one another than they are on the HabCam, an altimeter, an altitude sensor in the middle here, and then a TVL to provide accurate speed, along with additional pherometers, again matched to the HabCam system. So just some examples of what the stereo camera pairs look like out of ABIS. You can see some scallops on the seafloor, which is what we're after. And then we had really nice results in 2024. So 115,000 images collected over the course of 2 cruises. This is one of them. You can see 3 segments of AUV surveys between 9 nautical miles and 68 nautical miles, so representing between 1 and 2 days of surveying each. In this case, the vehicle was launched and recovered from the RV Sharp. So we're sort of intermediate in terms of long range. Most importantly for us is the images comply in terms of format, metadata, and quality with the existing processing pipeline for HabCam, and there were no statistically significant differences found in shell height estimates. So 7,000 of those images were included in the assessment relative to 80,000 from HabCam. So we're really excited about that. And this collaboration is continuing. We hope to be back out with NOAA in, I think it's a month and a half. All right. So those were ship launched and recovered surveys. Of course, there's lots of potential benefits. So like we talked about at the very beginning of this talk, to being able to launch from shore. And we've made some good progress in terms of operationalizing that idea. So this is a test from last fall where we launched the system in Buzzards Bay. It swam out to a wind farm site, specifically the South Fork site. Spent 35 hours on site, surveying back and forth between the turbines, and then returned for another 35 hours and was recovered back in Buzzards Bay. So the transit in this case was 100 kilometers in each way, executed at 1.5 knots. If you use the total usable capacity of 400 amp hours and transit versus survey burn rates, you can see the extra cost of running the cameras here in the 2 amp hours per hour versus 1.6 amp hours per hour. Then you get a maximum time on station of 145 hours. We didn't do that. We did 2 days, not the full 4 or 5 days, but we were on pace to do that. And that would yield a maximum survey distance of around 350 kilometers. So this is looking pretty viable. We're really excited about this, and we hope to move eventually to mostly shore launched launch and recovery, which would eliminate the constraints imposed by a ship. So and potentially yield scaling as well. So near shore launch and recovery, a couple more words on that. I'd say that the viability and the value really depend on the facilities you have and the vehicle handling requirements. Relative to, say, the Remus 600, these systems can be launched from a small boat and a small davit, and it was really important for us not to violate that. So adding additional batteries for these systems is not a good trade. Similarly, actually launching from shore, at least in Woods Hole, was also not a good trade. It's so little time to put them on a small vessel and get them out relative to dealing with them on a beach and sand and so forth, that we've found anyway that for our location, the right answer is to put them out on a small boat. One note on reliability. So, of course, reliability matters with all systems, particularly, I think, with long-range systems, but there are certain mitigation strategies that can be applied. So with the system here, with the plankton shadow graph imager, we had this one out in February of last year, and it made it out to the shelf break, turned around, and about a third of the way back in, we suffered a battery fault, which dramatically reduced the amount of energy available. So we were stuck with a vehicle out in February, uh, some 60 nautical miles offshore, and with weather that prevented our ability to go recover it. What we were able to do is use the buoyancy engine to sit the vehicle on the seafloor and have it periodically come up every 24 hours and just report back, which gave us the kind of time that we needed to wait for a favorable window and then go and get it. So you can build in contingency for, especially for these long range platforms, that buys you time. Finally, piloting multiple vehicles scales better than one-to-one. So by which I mean, it takes one person 4 hours a day, let's say, to pilot one of these vehicles. It takes one person maybe 5 hours to pilot two of them. So assuming that you're sort of regular operations. So there's real benefit to not only shore launch and recovery, but also having multiple vehicles in the water at the same time. All right, so just to summarize overall, the range equation is fundamental, but it can be mitigated with various strategies. I talked about a few of them. Firstly, increase the most simple in some ways is to increase the battery size, but I would say that that's only a good trade if it doesn't significantly alter the handling characteristics of the system and the concept of operations. You can manage power carefully by picking the right speed, turning things on and off, working with sort of multi-phase missions where transits are handled differently than surveying. And then ASV teams can be used for force multiplication and also as ship proxies, which enable some of these lower power platforms to do things that they wouldn't be able to do without a ship. For example, to navigate, as we discussed with the gliders, and in other ways to reduce hotel load. If I had one overall lesson, it's that reliability really is paramount. Most of this work is in a developmental, not an operational context. I think it's obvious in a operational context, of course, but in a developmental context, these failure mitigation strategies are really valuable. So robust over-the-air debugging was absolutely critical in all of these projects. But you need to build that in at the start. And then the safe or fallback behaviors that buy you time are also really important. Wave glider is another example where at one point we were operating off the coast of Oregon with heavy wildfire smoke, and the vehicle eventually just lost power and went dark. But to the credit of Liquid Robotics, when the sun started shining again, it came right back and resumed what it was doing. There's a lot of work that I went through today, and there's a huge number of people that I would like to thank. I can't go through them all, but just I thought I might go through their affiliations in any case. So we've had a longstanding collaboration with UW APL on the IUSBL project, and one person from JPL has been involved there as well. We've had good collaborations with the Northwest Fisheries Science Center and Northeast Fisheries Science Center, especially with the MBARI LRAUV work. We work closely with MBARI to keep those vehicles running and continue to increase our knowledge of them. And finally, we have a number of ships that were involved here, and I really want to thank the captains and crews for all their safe launches and recoveries of all these systems. And finally, I'd like to acknowledge the support of NOAA OER, the NOP program, NOAA SINAR, NOAA OACI, and also NSF. Thank you all very much.
Audience, we have time to answer your questions, and we already have had some questions come in. Our first question is, how long does it take between when the glider surfaces until recovery?
I'm not sure I quite understand the question. Between surfacing and diving again, or
I think this was asked either during case study 2 or 3, maybe. I'm not sure exactly what's being referred to.
Okay. The time on surface is dependent on, in particular, how much data you're pulling on and off. But I think it's sort of minutes to tens of minutes between dives is what we're experiencing. We did a lot of debugging over the air, so we had periods of time when the glider was on the surface for quite a bit of time.
Great, thank you. Our next question, have you experimented with repeated or even nested surveys on a long-range mapping survey, i.e. ASV AUV transit, a first mapping survey, then it identifies seafloor features and does follow-up detailed dives, examples like photos, H2O samples?
Yeah, I think that's where I would love this work to go. We have certainly done a lot of nested surveying in the context of either multiple dives from ships or within a single dive. We've worked on other projects with trying to telemeter up useful synopses of data that allow operators and scientists to make decisions about what to do with the AUV or without recovering it. But there's in principle no reason why you couldn't do that over with a long range system if you had the ability to talk to it via some kind of relay or perhaps when it came to the surface. But I think having a relay on the surface is uh, is really pretty potent there, especially in deep water, because otherwise you're talking about hours to transit back to the surface. And if you're, want to follow up on the whiff of a hydrothermal vent and find and take a photo of what's on the seafloor, then that's going to at best cost a lot of time. And at worst, you're just not going to be able to find your way back to where you were. So, yeah, I think that's the direction I would really love this to go. Yeah.
Our next question is, do you have plans to design a smaller version for rivers?
Smaller version of what?
This was asked during case study 4.
Case study 4, which was the LRAV. No.
All right. And then our next question, has there ever been a proposed RTG powered AUV?
Yeah, right. So this comes to the battery question, right? If we could just have better batteries, then some of this would go away. I am sure that there has been. It's problematic in the public sector, right? To use something that could uh, you know, fail in a way that would poison, result in radiation leak. So I'm sure it has been done. I think if I maybe talk a little bit about batteries. I mean, one of the, the battery thing has been something that people have been working on for a long time. Seawater batteries that harvest, say, the oxygen from the salt water, and thus like an internal combustion engine have half of their fuel available externally. And various versions of that exist and have been used. But the practicality of it is also really important, right? So being able to service these systems in a reasonable amount of time and the cost plays a role here too. Even if you could get a really long range system out there, if you can't use it more than once, then I think the value is reduced. If it's really really long range, like like an Argo float, then it starts to make sense again. But I'm not aware personally of any RTG powered AVs.
And then our next question, what is the average angle of ascent and descent for the vehicles?
Mm-hmm. Yeah, so for the gliders, which I think is what this question is referring to, 20 degrees is a typical glide angle.
Our next question is, has there been any ideas for an AUV that could park on the floor and
Mm.
act like an underwater turbine for charging?
Yeah, yeah, that's a cool idea. And there is there have been ideas along those lines. Like for example, there was a program not too long ago that was looking at trying to recharge at hydrothermal stations, so using a thermal gradient or other sources of power that might be available at hydrothermal sites, and sort of use them as gas stations for long range vehicles. So yeah, I think this again comes down to practicality, right? I mean, there's another really beautiful way to extend the range of gliders, in particular that Teledyne has built, which is this glider that harvests the Slocum glider, so, that harvests or Slocum concept, rather, I should say. They're all called Slocum gliders, but that harvests the original Slocum concept was to harvest energy from the thermal gradient uh, in the ocean. So using, I think wax was the working material, and as it expanded and contracted, it would actually push through drive a turbine, which would then be used to charge the batteries, and it works. And a prototype system, does exist. So for again, I think in the very low power context, and in fact, there's a float that works similarly that also does a similar kind of thing. So in the very low power context, it's possible. For higher power, the power density I think is hard to find. Like in the deep sea, I mean, how strong are the currents? You got 5 to 10 centimeters per second to work with, so it's hard to extract much energy out of that. So I think it's not that it's impossible, but I think the practicality of it is challenging.
And then our next question is, has funding for these projects been directly influenced by saving ship time, i.e., beyond the unique research values and capabilities? Are partners actively spending money developing these because hours of ship operations are super valuable.
Yeah, I think that in general, yes, if you include many other projects besides my own. In my case, I think we're getting close there with the LREVs in the context of the Scallop survey. So we're not there yet, but we're that's the closest project to being operational or getting on an operational footing.
Great. Thank you so much. And that is all of the questions that we have in the queue. Um, Thank you for presenting today, Mike, and thank you for organizing this event, Nina. Nina, do you have any last comments?
Yes, thank you. I just wanted to say thank you again to Dr. Jakuba for your amazing presentation. It was very interesting hearing about all the different case studies that you presented to us today. I also wanted to thank you, Cassandra, for facilitating the seminar. And finally, I wanted to let everyone know that the next NOAA Ocean Exploration Seminar, co hosted with the NOAA Library, will be on June 4th at 2 p.m. Eastern Time and will feature Doctors Andrea Quattrini and Alan Collins, who will discuss their work exploring the pelagic and benthic biodiversity in deep water habitats off the coast of Puerto Rico. So please mark your calendars and we'll send out more information shortly. And thank you all again for joining and have a wonderful rest of your day.